In this video, we're going to study the unit group of a finite field. Recall that in the last video, we introduced a field f of order 9, and the way that we got f was we extended the finite field z mod 3 by a root of the irreducible polynomial x squared plus 1, which we called alpha. So f consists of all linear combinations over z mod 3 of 1 and alpha, which is the root of that polynomial. So alpha squared plus 1 equals 0. That's a finite field. It has order 9. And in this video, we're just going to analyze the multiplicative group of units for f. So just as a reminder, in general, if f is any field, finite, infinite, characteristic 0, characteristic p, whatever, is any field, the set f star of non-zero elements forms a group under multiplication. Okay, why is that true? Why does that always form a group? Well, we know that multiplication in f, being a field, is associative. A field always contains an element 1, a multiplicative identity, and for each x belonging to f star, that is every x non-zero, x has an inverse. That's the definition of a field. So those are the three things that are required to be a field. And in fact, we can also say multiplication is commutative because we're in a field. So not only is f star a group, it's an abelian group. Okay, so that means that we have some foothold, at least in the finite case, for analyzing the structure of that abelian group, because we have a structure theorem for abelian groups. We have a classification. So what I'd like to do is figure out, if I have a field of order 9, then that means that f star, because it excludes 0, I can't seem to draw stars today, it's weird. F star is a group of order 8, because 0 doesn't belong to f star. So we're excluding that one element, but all other elements are in play. We have an abelian group of order 8. So the question is, what is the structure of f star? That is an interesting question. All right, so let's back out here, pull that up, and let's see if we can figure out the structure of this abelian group. So just as a reminder, if we have a abelian group of order 8, there's only a few choices for what it could be. So f star has to be isomorphic to one of the following. It could be isomorphic to z mod 8, which would be a cyclic group of order 8. It could be isomorphic to z2 plus z4. That would be a non-cyclic abelian group with elements of order 4 but no elements of order 8. Or it could be isomorphic to z2 plus z2 plus z2, which would mean it has only elements of order 2 and the identity. Those are the three choices that seem to be in play here. So how do we figure out which of these three options here is actually isomorphic to this group of units? Well, one way we can approach that is we can just do an experiment. Take an element of f star, find its order, and see if we can use that to eliminate any of the possibilities here. So I'm going to take an element which I don't know a whole lot about. Like if I take -1, that's certainly an element of f star, but I know what its order is already. That order is 2, and that's not going to help me differentiate among these. Any of these three alternatives here would have an element of order 2. Okay, so let's use a less familiar element then. Let's consider 1 plus alpha. That's certainly an element of f star. It's non-zero, and we can just start taking powers of it. So let's try taking the second power, just to verify whether that ends up being 1. Well, that's going to be 1 plus 2 alpha plus alpha squared. Alpha squared plus 1 is equal to 0, so alpha squared is -1. Let's just have that up here for whenever we need it. So this is the same as 1 plus 2 alpha plus -1 or -1. That's 2 alpha. Okay, great. So 1 plus alpha squared is not 1, it is 2 alpha. That means that the order of 1 plus alpha is greater than 2. So I already have an element of order greater than 2, which rules out z2 plus z2 plus z2 as a possibility because that has no elements of order greater than 2. Awesome. Amazing what we can do with just a little bit of work here. All right. So let's keep going and see if we can find what the order of 1 plus alpha would be. Now I could try multiplying 2 alpha by 1 plus alpha again and see what 1 plus alpha cubed is. But I already know that the order of 1 plus alpha is not going to be 3 because I'm in a group of order 8 and you can't have an element of order 3 in a group of order 8. So let's just try taking 1 plus alpha to the 4th, which is the same thing as 1 plus alpha squared. And we already figured 1 plus alpha squared is 2 alpha, so 2 alpha squared, that's going to be 4 alpha squared. And alpha squared is still -1. So that's 4 times -1. So that's -4. And in Z mod 3, or over characteristic 3, that's equivalent to 2, which is still not 1. Okay, so 1 plus alpha doesn't even have order 4. The order is greater than 4, which means I can rule out this possibility as well. Z2 plus Z4 has elements of order at most 4. Okay, let's just verify, even though we know this is going to work because we're in a group of order 8, let's verify that 1 plus alpha to the 8th is actually the identity, or 1. 1 plus alpha to the 8th, that's going to be 1 plus alpha to the 4th squared, which is, let's see, that's 2 squared, because 1 plus alpha to the 4th was 2. That's 4, and over characteristic 3, that is equivalent to 1. Yay! So the order of 1 plus alpha is 8, which means we have a cyclic group here of order 8, and it is the group generated by 1 plus alpha. Now we could go a step further and actually create a little diagram that shows all of the elements of this group in cyclic order. So I could zoom this out. And make a map of the powers of 1 plus alpha. So I'm going to start with 1 here. So I'm going to put that in the 12 o'clock position. So this is 1 plus alpha to the 0. And then I've got 1 plus alpha. So that's 1 plus alpha to the 1st. And then the second power of that was 2 alpha. So I'll put that over here at the 3 o'clock position. Move this over a bit. There we go. So that was 1 plus alpha squared. And then at the 6 o'clock position, I'm going to skip 1 for now and put 2 down here. That was 1 plus alpha to the 4th. And now let's fill in the rest. Okay, so 2 alpha times 1 plus alpha. That's going to be what? That's 2 alpha plus 2 alpha squared. Alpha squared is -1, so that's 2 alpha minus 2, which is the same as 2 alpha plus 1, or 1 plus 2 alpha. So that's 1 plus alpha to the 3rd. And now I'm just going to make the rest of my work easier by using what I know already about powers of 1 plus alpha. I know that 1 plus alpha to the 4th is 2. That's the same as -1. In fact, it's customary sometimes when working over a field of, or working in a field of characteristic 3, instead of using the coefficient 2, use the coefficient -1. So this is really -1, which means what I have at the, I don't know what o'clock this is. It's I guess the southwest position, 1 plus alpha to the 5th. That's going to be 1 plus alpha times 1 plus alpha to the 4th. That's -1. So that's just going to be -1 minus alpha, or if I want to call it this, I can call it 2 plus 2 alpha. And then up here I have -2 alpha, which is just alpha. And then up here I have the opposite of 1 plus 2 alpha, which is 2 plus alpha. And now I have a diagram showing all 8 powers of 1 plus alpha, which now makes it easy to determine the answers to questions like, well, let's say I take 1 plus 2 alpha, and I want its 7th power. Well, 1 plus 2 alpha, I can read from my diagram that's 1 plus alpha to the third to the 7th. So that's 1 plus alpha to the 21st. And then, well, I don't know the 21st power. I don't have that on here, but I know the 8th power is 1. So I could just say that's the same thing as 1 plus alpha to the 16th, which is to the 8th squared, and then times 1 plus alpha to the 5th. And 1 plus alpha to the 5th was 2 plus 2 alpha. Just separate that off there. There we go. So 1 plus alpha to the 7th is 2 plus 2 alpha. So this little wheel here makes calculations, multiplicative calculations, within this unit group relatively easy to do. Okay, one more thing before I end the video. In this video we showed that the unit group of a field of order 9, which has order 8, so that's this F star here, this was cyclic. It turns out that's not a coincidence. It's not something that we even have to experiment to find out about a finite field. It turns out that for every finite field, the multiplicative group of units is cyclic. That's a theorem that we will prove later.